Okay, so I want to go back and review some of the physiology of oxygen delivery and oxygen consumption. Uh, Even though this is perhaps revision from the primary and things, I think it's an important sort of underpinning of stuff about hemodynamic monitoring and hemodynamic management and the management of patients in shock and the cardiac patients that I want to talk some more about over the next few weeks. So we start by thinking about the oxygen content of the blood. The oxygen's in two forms. It's mostly bound to hemoglobin, and there's a little bit that's dissolved in the blood. But the dissolved fraction is really fairly trivial, so we're just going to ignore that for the purpose of the talk and the calculations. And we're just going to think about the oxygen that's bound to hemoglobin. So the oxygen content then is determined by the hemoglobin concentration and also by the amount of oxygen that hemoglobin combines. So that's 1.34 mils of oxygen per gram of hemoglobin. That figure varies a bit depending which book you look at, but about 1.3. And then also the saturation of the hemoglobin. So if we stick some numbers in there, if we have a hemoglobin concentration of 150 grams per litre, multiply that by the maximum capacity is 1.34 mils of oxygen per gram of hemoglobin, and the percentage saturation of say 0.98, then that brings us out to about 200 mils of oxygen per litre of blood. So the book's going to say the normal range for arterial oxygen content is about sort of 16 to 22 mils per decilitre, or 160 to 220 mils per litre of blood. Now, obviously, this is based on some assumptions that aren't true in a lot of the patients that we look after. Hemoglobin of 150 would be pretty rare in the ICU population, but just go with it for the purpose of the calculations. Now, the oxygen delivery then is depends on the oxygen content of the blood multiplied by the cardiac output. So it's the oxygen content in mils per litre times the cardiac output in litres per minute will give you oxygen delivery in mils per minute. So again, to stick some numbers in there, if we've got the oxygen content of 200 mils per litre and the standard sort of cardiac output of 5 litres per minute, then the oxygen delivery is about 1,000 mils per minute. And again, the normal range about sort of 900 to 1,100 mils of oxygen per minute. In practice, some of these hemodynamic variables and things like cardiac output and things, they're all indexed to body surface area. Obviously, a big person is going to have bigger numbers than a small person. So to try and standardise that, a lot of them are indexed to the body surface area. So in terms of actually working out or knowing the oxygen consumption for the body, you could measure this from the inspired and expired oxygen concentrations and also the minute ventilation, and that way you could work out how much oxygen is consumed in a minute. Alternatively, it depends what variables you know. So alternatively, you could work out or you could measure the arterial oxygen content from an arterial gas and the mixed venous oxygen content from the pulmonary artery, and the difference between those two, certainly multiplied by the cardiac output, will give you the amount of oxygen that's been consumed by the body each minute. So in terms of that mixed venous oxygen content, it's the same equation, but just using the mixed venous saturation from the pulmonary artery blood rather than the arterial saturation. So if we just rearrange that equation, take the hemoglobin and the constant out, if we use a mixed venous saturation of 75%, then we come up with oxygen consumption of 250 mils a minute. So that's the sort of standard healthy person oxygen consumption a minute. It's around about in the range of 3 to 5 mils per kilo per minute, if you think about it in terms of body weight. So basically, if we know what the mixed venous saturation is, and obviously we know the arterial saturation, then we can calculate the oxygen consumption. So what does it mean to say that the mixed venous saturation is either 75% or 66% or 50%? So this is what it sort of comes down to, is about the oxygen extraction ratio, or the ratio between the oxygen delivery and the oxygen consumption. So if you've got a litre a minute of oxygen delivery and 200 mils a minute of oxygen consumption, the ratio of consumption delivery is about 1 to 5. Assuming that the arterial blood is 100% saturated to start with, then the mixed venous saturation is going to be 80%, because 20% of the oxygen has been taken up and extracted and consumed. So just going through all these, if the delivery of oxygen is a litre per minute and the consumption is 250 mils a minute, the ratio is about 1 to 4, and the mixed venous saturation will be about 75%, and that's the normal sort of range. And then as you get further down, if the ratio is sort of 1 to 3, that's a mixed venous saturation of 66%, and a ratio of 1 to 2, mixed venous saturation of 50%. So the oxygen consumption is related to the oxygen delivery by the oxygen extraction ratio. So if the oxygen delivery is 1,000 mils per minute and the oxygen extraction ratio is 1/4, then the oxygen consumption must be 250 mils a minute. So in the normal, relatively healthy person, if the oxygen consumption is increased for some reason, the metabolism of the body is increased, the demand's increased, then the oxygen delivery is increased to keep up with it, largely by increasing the cardiac output, although there's also the option of increasing the extraction ratio. But in healthy people, it's largely achieved by increasing the cardiac output, if you've got the ability to increase your cardiac output. Now, the maximum oxygen extraction ratio is about 50 to 60%, which corresponds to mixed venous saturation of about 50 or 40%, respectively. Now, I'm not entirely sure why you can't really extract more oxygen than that, although I suspect that it's probably related to the sigmoid shape of the oxygen dissociation curve. So as you get down towards the bottom of the curve and the blood's more, the hemoglobin gets more hypoxic, it's harder to unload the last couple of oxygen molecules from the hemoglobin. Anyway, if the metabolic demands of the tissues exceed the amount of oxygen that you're able to deliver by the combination of the maximum cardiac output the patient can generate and also the maximum oxygen extraction that can be achieved, then the tissues are going to become sort of hypoxic. Their metabolism is going to become anaerobic. There's going to be subgeneration of lactate, and there's going to be damage to the cell membranes, energy depletion, ATP depletion, failure of the transport proteins and things, and ultimately cell death and organ dysfunction. Now, I've put there just about the fine print, some things just to remember. We know that in sepsis, which obviously is only one kind of shock that we're talking about, but in sepsis, the oxygen delivery is not necessarily decreased. Sometimes it's more of a problem with the mitochondrial oxygen utilization rather than a problem with oxygen delivery. And also some of the lactate that's produced in sepsis may not be due to tissue hypoxia either. So just some fine points to keep in mind. So if we just think about a couple of examples, and I'm sure you're expecting I was going to get to this graph, and this is sort of the key part of it all. If you're thinking about, for example, an anaesthetized well patient, they've got high oxygen delivery, their FiO2 is good, their hemoglobin's good, they're maybe a little bit tachycardic, so their cardiac output's up, and they're sedated, analgesied, anaesthetized, maybe the operation hasn't started yet, so they've actually got very low oxygen consumption. Then they're going to have a low oxygen extraction ratio and consequently a pretty high mixed venous oxygen saturation. So comparing that slightly different situation of the person who's doing some aerobic exercise, some heavy aerobic exercise, so they're going to have a very high oxygen extraction or oxygen consumption, sorry, uh, and the body's going to meet that high oxygen consumption by giving them a high oxygen delivery, and they're going to achieve that by having very high cardiac output. Assuming they're still aerobic rather than anaerobic, their oxygen extraction ratio hopefully is still going to be in the range of 30 to 40%, and the mixed venous saturation correspondingly will be sort of 60 to 70%. So if we look at this graph now with some of the thinking about some of the sick patients that we look after, and if their oxygen consumption remains fairly constant for the purpose of the exercise, but their oxygen delivery is falling, which is mainly going to be due to a fall in cardiac output. Although if you just remember the other things we talked about at the start about oxygen delivery is about the hemoglobin and the saturation, so those things could fall and affect the oxygen delivery as well. But it's mainly the cardiac output in the short term that we're thinking about. So to start off with the normal sort of situation, the ratio between oxygen consumption and oxygen delivery is about 1 to 4, as I've said, and that gives us a mixed venous oxygen saturation of about 75%, which is normal. Now, as the oxygen delivery falls, so again, assuming that's mostly related to the cardiac output, then to achieve the same, or to supply the tissues with that same amount of oxygen consumption, then the oxygen extraction ratio increases, and so you get to a point where the ratio between consumption and delivery is about 1 to 2, and the mixed venous saturation is about 50%. And as I said, that's the maximum amount of oxygen extraction that can occur. So this is referred to as the critical DO2, or the critical level of oxygen delivery, which is the lowest DO2 that's capable of fully supporting aerobic metabolism. So once the oxygen delivery falls below that, then the tissues are increasingly going to become anaerobic. The other key term here is that once the extraction ratio is maximised, then further falls in the oxygen delivery is said to cause supply-dependent oxygen consumption. So essentially, the tissues are using everything they get, but what they get is limited by the supply. So this idea of supply-dependent oxygen consumption is a key concept. So once the oxygen delivery, again presumably mostly cardiac output, falls further than this critical DO2, then as I've said, there'll be increased proportion of the metabolism will be anaerobic, and there'll be decreased ATP production. Remember that with aerobic metabolism, you're getting about 36 ATPs per glucose, and with anaerobic metabolism, you're only getting about 2 ATPs per glucose molecule. But having said that, the ratio, the extraction ratio will still be sort of 50%. It's just that there's not going to be much oxygen delivered for the tissues to be able to extract. So the last thing I just wanted to mention here is about the relationship between central venous oxygen saturations and mixed venous oxygen saturations. So remember, the mixed venous from the pulmonary artery, very rarely do we have a PA catheter in, and so we'll often be taking blood from the SVC from a central line and using that as a kind of surrogate. Now, there's a lot of contention about whether that's actually valid, and the saturation that you get from the central venous blood compared to the mixed venous blood kind of depends on the relative proportions of blood flow to the upper and lower body, and the relative oxygen extraction from the blood in the SVC and the blood in the IVC. And obviously those two things are mixed together to become the mixed venous blood in the pulmonary artery. So the conventional wisdom is that the saturation in the mixed venous blood in the pulmonary artery is about 2 to 10% higher than the central venous saturation. So if we're worried about mixed venous saturation less than 65, then we're happy with the threshold of about 60 for the central venous blood. But I mean, we don't really know. the variables, as I said at the start there, it kind of depends a lot where the blood's going and how much is extracted, in the upper body and the lower body. And then in shock, these things have probably changed further. So in shock, as to how much blood goes to the brain, how much goes to the gut and the kidneys, and then how much oxygen is extracted by each of those organs, we don't really know. So the best argument you can sort of say is that you're just using the central venous sats to follow the trends and the response to therapy. And I've attached an article where they'd done some experiments, particularly animal experiments, and I think some human experiments, kind of comparing both. And actually, it's often the other way around, with the central venous sats being higher than the mixed venous sats. So the ratio is definitely not fixed. It's not clear, and it probably changes when patients are sick. So the best that you can really say is that you're just following the trends in the central venous sats, because the trends between the two certainly seem to correlate, even if the numbers are different. Okay, so hopefully we'll build on this in coming tutes about hemodynamic monitoring and hemodynamic management. Thanks.